Hello everyone, I'm Lynn from Microelectronics. Welcome to our ToF camera design tips. Today we'll focus on key technical challenges and Goermicro Vzense's solutions. As mentioned in previous videos, a time-of-flight camera mainly consists of light emitter, control unit, time-of-flight sensor, and processing unit. Some also integrate RGB cameras. The two core components are the light emitter and time-of-flight sensor. The emitter can use laser, infrared, or visible light, with most current ToF cameras using near-infrared. 3D depth data is calculated by measuring the time for emitted light to reflect back from the scene. There are different types of ToF, including direct and indirect. Today we'll focus on indirect ToF, which has two modes: continuous wave and pulse. For continuous wave indirect ToF, the basic principle is modulating light into square waves at a specific frequency, then measuring phase offset between emitted and received signals to calculate distance. How to measure phase offset? The camera modulates the laser emitter into 4 phase energy patterns: 0 degrees, 90 degrees, 180 degrees, 270 degrees, and calculates phase offset from integrated energy values. For pulse indirect ToF, it emits repeated pulse signals and analyzes pulse phase to obtain depth. To get flight time, the laser emitter is modulated into 2 phase energy patterns, 0 degrees and 180 degrees, while also collecting background light when no pulse is emitted. Flight time T is calculated from the ratios. How to choose between continuous wave and pulse iToF. We can compare them in terms of power consumption, anti-light interference capability, frame rate accuracy, jitter performance. Both have advantages. Goermicro Vzense's ToF cameras cover both technologies: DS series, continuous wave, higher accuracy, uses Sony Infineon sensors; MYX series, pulsed, higher frame rate, uses Nuvoton sensors. Our first tip: understand which applications ToF is best suited for. Our cameras work best at 0.1 to 5 meter range with approximately 5 mm accuracy error, making them ideal for short-range robot obstacle avoidance, automated material handling, and people counting, but not for high-detail 3D scanning like optical metrology. To maximize ToF performance, consider lighting first. Our spectral response curve highlights 940 nanometer wavelength, important because sunlight naturally attenuates at this wavelength. ToF cameras also use bandpass filters to block other sunlight interference. Without filters, sunlight can easily saturate the signal. For outdoor use, choose models with bandpass filters and 940 nanometer emission. Next is motion blur. For continuous wave ToF, each depth frame actually consists of 4 phase-shifted subframes. If object's camera move too fast, this can cause 3D distortion. Generally, motion speed threshold depends on frame rate and exposure time. Our pulsed NYX series fundamentally solves this with high duty cycle pulses, lower SNR, shorter exposure, and higher frame rate. There's an example comparing DS86 and NYX 650 in hand-waving tests. Both show high accuracy when static, DS slightly better. During fast motion, NYX maintains stable images with minimal blur. Now let's move on to specular and non-reflective objects. Tires are a classic example with both low and high reflectivity areas. Testing different exposure settings and HDR modes on Vzense's camera reveals. With HDR off, increasing exposure improves low reflectivity surfaces, but excessive exposure causes high reflectivity overexposure. Our ToF camera's HDR mode solves this. At 1000 microseconds exposure, HDR preserves details in both low-high reflectivity areas. Finally, multipath reflections and flying pixels. Multipath occurs when light reflects off multiple surfaces before returning. Example: concave corners cause detail loss. Solution: minimize concave angles and remove unnecessary reflective objects. Flying pixels are erroneous points in 3D clouds, typically at depth. Discontinuities, object edges, where foreground-background light mixes, creating false depth values. Solutions: optimize ambient light, remove reflective objects, and use flying pixel filters. Our software includes 4 key filters: confidence filter, spatial filter, flying pixel filter, and time filter. Confidence filter is a high-pass filtering technique that removes low-confidence depth pixels based on signal quality metrics. Spatial filter is a kernel-based convolution operation that processes local pixel neighborhoods to smooth noise or enhance spatial features. Flying pixel filter is an edge-aware median filter that eliminates flying pixels at depth discontinuities through neighborhood median validation. Time filter is a temporal averaging method that reduces noise by integrating depth frames over time while preserving scene coherence. That's all for today's video. We hope you found it helpful. For more details, please visit our website or leave your comments below.